Yes, hello everyone. I'm Agnar Sivertsen. I'm a senior scientist at the Drones and Autonomous System Group at NORCE Research. NORCE is a Norwegian research institute. We have the main office in Bergen, but I'm located in Tromsø. I also have Trond Løke with me from Norwegian Elektro Optikk. Trond, are you there?
I'm here, yeah.
So me and Trond, we will have this session together, and the first, so this is the schedule for our 2 days. We are on day 1 now. So before the lunch, we will do some basics, remote sensing, and also introduction to hyperspectral imaging. After lunch, Trond will tell you all there is about key quality parameters in hyperspectral remote sensing. And after coffee, we will have a hardware overview and a virtual field excursion. So I'm looking forward to that. But Trond, maybe you can introduce yourself first.
Yep. So yeah, I'm Trond Løke. I'm the CEO of Norsk Elektro. Yeah, started in 2002 in this field. Took my master's at Norsk Elektro, and yeah, started to get to know you, Agnar, in 2004 when you worked at Fiskeriforskning. Actually, Agnar bought or purchased the first hyperspectral camera that we sold in 2004 when he worked at Fiskeriforskning. Yeah, so we have a long collaboration from fish to remote sensing now. So yeah, and yeah, so I started as a scientist right after my master's and been senior scientist, CTO, and then now CEO. But I said I have a very big focus on the technical part of what we're doing.
Okay, good, Trond. So I can just add that I worked several years with hyperspectral imaging in the food industry and developed a system for online grading of fish product and have a good understanding of hyperspectral imaging. And then the last few years I have moved to remote sensing or aerial remote sensing using hyperspectral imaging, and that's a whole different ball game. So that is what we are going to focus on today. But first, I will have some very basic definitions that we will use or you will hear about later in this presentation. This is probably well known to most of you, but even though here it is. So by remote sensing, we define it as the process of monitoring physical characteristics of an area or an object. And we do it by measuring its reflected or radiated or emitted radiation, and we do it from a distance. This distance can be short or long, and we divide it in 3 categories usually. And during this week, we will hear about all these 3 categories. So on Thursday, I believe Hans Tømmervik is going to tell you about ground-based remote sensing. And on Wednesday, we will hear about the Prisma satellite, spaceborne remote sensing. And today, we'll talk about airborne remote sensing. So the first category is when we have sensors mounted on masts or tripods. Close to the ground, it can be from a few centimeters to tens of meters. These systems are very important, especially for calibrating and validating airborne and spaceborne remote sensing. And then we have airborne remote sensing, or also called aerial remote sensing. It's done from an airborne platform, of course. And today I would say that manned aircrafts are the main aerial platform for doing this. Main reason is that you can carry more and better equipment on a manned aircraft than you can on alternative platforms, like a drone, for instance, which is really a popular incoming platform these days. Spaceborne remote sensing is the main category. These are satellites. A lot of benefits with using a satellite. One thing is it has a fixed viewing geometry, and you have also a fixed orbit. Of course, the disadvantage of doing this is that the orbit is fixed, and you can't, for instance, reschedule your mission depending on clouds and so forth. So then I will go through three or four very important terms. The first you will hear about is irradiance. Irradiance is a unit measured in watts per square meter. It is the power that is received by an area or an object from the sun, sky, nearby objects or clouds. So on the top right here, I have a simple sketch. We have the direct component from the sun. We also have a scattered components from clouds and the atmosphere, and we have a sensor. Usually this angle between the sun, we call it the zenith angle. So it's the angle between the sun and the zenith, and the same with the sensor. In addition to this, we also have the azimuth angle. This is also referred to as incoming light or sometimes solar irradiance. And then we have radiance. This is the measurement, or this is the quantity we measure with our spectrometer. It is watt per square meter per steradian, which steradian is a spatial or solid angle. And it's a directional quantity. And what I mean by that is it depends on, it can depend on the direction you measure it from. And there are potential confusing statements here. So the popular one is probably that, so the radiance received from a surface by a detector or your eye does not change with altitude. The common misconception is that people think that when you move away from an area or an object, you should receive less light, since the emitted or the received flux is reduced. But as you move away, the area you observe is also increasing in size, similarly to the reduction in received flux. So the total energy or intensity that you observe or detect is the same, independently of the distance. And that is if we don't think about atmospheric losses, for instance. The second confusing statement is that you can often hear that we say that we can improve the signal to noise ratio in aerial remote sensing, especially by flying higher. And the reason for that, I will try to explain here. It depends on flights with altitude, exposure time, and motion blur. So first, the pixel size is fixed when it comes to the angle or field of view, angle field of view. And the field of view in meters, for instance, on the ground can be calculated like this. So when you move higher, the field of view or the footprint of a pixel is increasing. So that's the first thing. The second thing is that motion blur. Motion blur is the process when we are recording or exposing the sensor or a camera, and the aircraft moves along the ground. These pixels are smeared in the flight direction, and you will get an average measurement along the flight line. So typically, we accept motion blur when it's below 0.5 pixel, and 0.5 pixel that can be converted to meters using this equation at the top here. And when we have these three definitions, we can calculate a minimum accepted altitude as a function of ground speed, exposure time, and pixel field of view. Yeah, this is the equation for doing that. And on the right here, I have plotted this minimum altitude given three different exposure times for the high-specs camera that is in the door here. So for instance, if we expose really fast at 2.5 millisecond and we fly at 150 knots, this is ground speed, we see that the minimum altitude we can fly at while keeping the motion blur below 0.5 pixel is 2000 feet. So by increasing the exposure time, we improve the signal to noise ratio. So we expose longer, but then you will see that if it increases to 6.5 millisecond, we have to fly higher than 5,000 feet to keep the motion blur below 0.5 pixel. So these are calculations we do in the mission planning phase. So for instance, there can be a customer who says that he wants half a meter resolution, and that determines the maximum altitude we can fly on, and we can also then calculate the maximum exposure time we can use to achieve this. Yeah, so just a plot showing the this is the high specs ground resolution as a function of altitude, and the ground resolution across track differs from the ground resolution along track. So the along track ground resolution is half the across track ground resolution. So from to give you numbers, from 3,000 feet, which is a typical altitude we fly at for having high resolution data, we have 30 centimeter ground resolution across track and 60 centimeter ground resolution along track. And we can oversample this along track. So we can select exposure time so that we oversample with 50% along track. So I have two more terms to define. So reflectance. Reflectance is it's the ratio of the outgoing light from an object or area to the incoming amount of radiant flux. It's a function of wavelength, and we often refer to it as spectral reflectance. And reflectance is a surface or object property, and it's independent of irradiance. So we often want to calculate or convert our radiance measurement, which we get from the spectrometer directly, to reflectance. And there are different ways of doing that. I will come back to that in the next slide. But it's a quantity we want to end up with. But then there are properties with natural materials that makes the light we receive dependent on both the viewing geometry and the illumination geometry, and that is referred to as the bidirectional reflectance distribution function, BRDF. So this function has spectral properties, but if we consider reflectance only, this has 4 parameters. So there are 2 zenith and 2 azimuth angles, meaning that you have all possible positions of your sensor and all possible positions of your light source. So this is a 3D function, and also a property of natural materials and surfaces. So for instance, you have probably, when you watch soccer on your TV, you will see these striped patterns on the turf when you are viewing the lawn from the side like this. And this has to do with the way the grass is lying relative to you and the light source. So just the spectral properties, as I mentioned, in addition to that the intensity varies depending on the view and illumination geometry. The spectral property can also vary. And on the right here, we have an example of lawn grass measured at 10, 20, 30, 50, and 60 degrees viewing zenith angle in the principal plane. That means that the light source and the receiver is in the same plane. We are illuminating we are using a zenith angle of 45 degrees, and we are varying this receiving zenith angle. And if you look at this plot, you can see that 0 degrees is nadir, meaning that the camera is looking straight down. We have less reflectance in the visible near infrared range relative to the infrared range than if we view this at minus 60 degrees zenith angle, for instance. So this effect, I just want to show you that it can be significant, especially when you are if you are comparing scenes recording under different conditions. I mean, sun angle, viewing geometry, and if there are clouds or not. And but in modeling or classification work, this effect is usually considered as natural variation. So my last slide is on atmospheric correction. So the spectral radiance we measure from a surface or an object, it depends on the irradiance that hits this area. And to be able to calculate our radiance measurements to reflectance, we need to know the irradiance. And there are different methods for getting the irradiance. One simple one is to have a irradiance sensor on the ground collecting the light hitting the ground. So this is a spectrometer with something called a cosinus collector, collecting the light from all angles on the ground, giving you a spectra. We can have a irradiance sensor on top of the aircraft or a drone, collecting the incoming light on top of the aircraft and using that as the irradiance also on the ground. Very common way of calibrating satellite data is to use ground targets or areas with known spectral reflectance. So this can be a sand area or a roof or something else that we know the spectral reflectance of. And then the last part here is a model-based approach, where you try to estimate the spectral irradiance at ground level using model of the atmosphere. And there are software for doing this, and one available software is this ATCore package by RESA. I think Trond is going to follow up on an introduction to hyperspectral imaging.
Okay, then I will start. Yeah, so as we mentioned in the intro, I'm coming from Norsk Elektro Optikk. We are a privately owned research establishment, or research company in Oslo. We are doing one of our strategies is to do actually high risk research, and the high risk is both financially and technically. So we are not as normal commercial company where we only make commercial products. We're also doing a lot of European research projects and so on. So currently we are selling and designing new cameras for airborne, UV, field lab, and industrial. And actually we just got a project making a in-orbit demonstrator for ESA. I will actually start with we had a summer party a few years ago where we're going to introduce hyperspectral, what it was. So I will start my slides with that presentation.
There is nothing wrong with your television. Do not attempt to adjust the picture. We are now controlling the transmission.
Fun way to present what hyperspectral imaging is. But yeah, hyperspectral imaging is, as Agnar said, is combining imaging and spectrometry. So yeah, basically when you're designing a hyperspectral system, you want an image, 2D image, and where each pixel in that image has a lot of wavelength colors. And the architecture for doing that can be very different. You can have push broom, whisk broom, snapshot, and so on. I will talk more about that after lunch. But the end product is the same, an image cube in 3 dimensions. When I was listening to all of you guys' intro or bio, then I understood that probably these slides are not you know this already, right? But I like to use Torbjørn Skauli's example when I'm telling people for the first time what hyperspectral imaging is. So I will go quickly through it. So here you have 4 plants. One is artificial, and you have a Lego person, which is a missing person application. So as you know, you have if you have a monochrome camera, if you look at the spectra here on the right, that's a spectral from 400 nanometers to 1000 nanometers. For a monochromatic sensor, basically that's is sensitive from 400 to around 800-900 nanometers, and you get like a grayscale image based on the information in that wavelength area. For an RGB camera, like you have in your phones, you will have 3 areas, broad areas, in the blue, green, and red part. And while for a hyperspectral, right, you're getting what you're seeing here, the yellow spectra, so a spectral signature with several hundred bands typically. The definition between multispectral and hyperspectral is continuous discussion. There is an ongoing standardization project in IEEE P4001 where we are defining or trying to define where the limit between multispectral and hyperspectral goes. Yeah, so here there are some plots on the right side here from this scene where you see some vegetation spectra. This is a bit in the way, but you can see there's some vegetation spectra. There is some plastic spectra from the Lego person. And what you can see here from vegetation, right, is that you have the red edge around 700 nanometers. You have a big increase in the radiance, which is due to chlorophyll in the plant. Yeah, I'll come back to that. So how can we exploit spectral imaging? Yeah, of course, you can do a manual inspection, but that's not very good because you cannot visualize 200 bands to the human eye. You can do a band selection, just looking at each band separately, like we're doing here. Here you're looking at the energy in 473 nanometers. Here you're looking at the energy in 547, that's the green band. And in the green band, all 4 plans look the same. 621 is in the red band. Still, they're looking quite similar, because this is what your eye is seeing, right? And in the 681, you can start to see differences between the 4 plans. Yeah, so if you go to 770, that's on top of the chlorophyll edge. It's very easy to spot the difference between the 4 plants, because one plastic plant does not have chlorophyll and has a lot lower radiance value or reflectance value also in that wavelength. So then, yeah, you can do some simple classification to classify what is a plant, what is not a plant, and what is some other classes here as well. You can also exploit it in a different way, for example, which is, Torben Skavle is working for FFI, which is a very relevant application for them, anomaly detection, looking for spectral signatures that are unique from the background. And if you run it on CRX or anomaly detection on this image, where the intensity in this grayscale image is the probability of the pixel being part of the background or not. The higher intensity, the lower probability. So then you can see that the Lego person is lighting up, meaning that it's a very high probability that this is not part of the background spectral signature. And how you define a background spectral signature, of course, that's part of the algorithm that, yeah, you have many different anomaly detection algorithms, and FFI, they have their own, right? Yeah, other ways you can do change detection, like you fly over the same area many times, yeah, where you can see disturbances on ground, added removed objects, yeah, and quantitative analysis, right, where you can estimate physical scene parameters like concentration of chemicals, identification of pigments, and amount of biomass, for example. But what all of these things need, right? You cannot have the camera itself and not a processing unit. So you need to be able to process the image before you can present the results. That's why hyperspectral imaging is mostly sold to researchers, right? That is actually developing the algorithm to present the end solution. This is changing, has been changing over the last 5 years at least, where suppliers like us and others are supplying the full chain to an end user solution. Yeah, I'm an expert on cameras. I'm not an expert on all of these applications. So yeah, probably some of you might also even have been working on some of the slides that I'm presenting. So you have to excuse me if I'm saying something wrong. But this is to the best of my knowledge. I just gathered here some slides from our customers. Yeah, so here is for field application, just showing 3 installations where there's a French customer inside a tunnel looking at mineral classification. There's some military application, I think it's in Turkey. You have in Slovenia, someone looking at an apple farm. Yeah, in Australia, we're doing mineral classification of different kind of mineral. This is from CSIRO, from a tripod, and here it's combined with a terrestrial LiDAR. I think this is from 2008, if I remember correctly. So some old images. For FFI, for example, you have a detection of leftover explosive in the shooting range. We've done some experiments with the sphere spectral region. So this is not the same camera as Agnar has. NORCE has the one from 400 to 1000 nanometer, while for explosives, the one from 950 to 2500 is the best one to use. We can detect and discriminate between the different types of explosives as well. Yeah, and here are some spectral signatures of different kinds of explosives. We also did some tests. This is not, so we recently moved to Bryn, and this is actually from the place we had our offices before the previous place at the Norsk at Svalbard, where we had a person with some ammonium nitrate residues on their clothes, and some training data here, where we can detect it from 70-meter distance that they have residues of ammonium nitrate on them. Yeah, GFZ. Agnar is here worked for GFZ before. Yeah, they have been our customers for 12 years now, doing a lot in the field of geology, and the rare earth elements is one of them. University of Alaska as well, doing mineral classification from tripod. This is from Siper in Norway. I think they are part of NORCE now. This is combining hyperspectral and LiDAR, trying to differentiate between limestone and dolomite. And here they have overlaid the classified hyperspectral image on the LiDAR data. Yeah, here is waste from mines. I think these piles here, where they are looking at iron and zinc mapping. Iron on the left here and zinc on the right. So spectroscopy of beach seedlings under dryness test. So I don't know much about the experiment, but yeah, here you have some water thickness and chlorophyll content on the right and left side. This is from a crane, I think, above the plants. Same here, you have wheat nitrogen content. And then some airborne applications, which is what we're going to focus on for the next few sessions now. Yeah, there is a lot of applications. Yeah, geology is one of the large ones, definitely for the SWE region. Forestry mapping, precision agriculture, urban mapping, military and defense is quite large. Search and rescue, oil spills, environmental monitoring, and so on. And who is buying these systems, right? It's universities, governmental research institutes, and remote sensing companies, mostly. And more and more also actually end users or companies that are delivering a service, for example, in the remote sensing industry. Yeah, this is just some quick photos I found of some of the platforms that we are mounted on. I would say that the most normal airborne platforms are Cessnas like this, 402, and Pipers like this. But it's many different, like we have mounted it on a flying moped in China, an airship in Germany, and Chinese, now Russian aircraft in China that you have to start with a gun. So it's very, very different platforms. And UV platforms as well, many different platforms. But here it's we have a larger responsibility, right, for airborne than the customer supplies usually the platform, right? We have delivered a full aircraft before, but usually it's the customer that has the aircraft, while for UAV, more customers buy the full solution from us. So we have to certify that the solution is the UAV platform is also high quality. So here's just shown some copter solutions, and yeah, we also have fixed wing solutions. Here is a vineyard application. This is from Fraunhofer IFF, I believe. Looking at diseases, they try to detect it at an early stage so that they can prevent it from spreading to the whole or to all the plants. Again, also combining with the here, I don't think it's LiDAR, is photogrammetry. So they have been building up the 3D model with the RGB images. 3 species mapping. This is from 2XL. I have some more slides from 2XL in UK later on. But this is combining spectral algorithms that are doing spectral processing and also machine learning. Same kind of application, but done by DLR in Germany, flown at a higher altitude, a larger scale. Then we have a company in France, Actimar, and another company also in France, Hytech. I have done a lot over the last, I would say, I think they purchased in 2009, so the last 12 years on oil spill characterization, where they can detect the oil spills. They can detect or find the thickness and emulsion rate of the oil. That means that they can also, when they can detect the thickness right, they can also find the volume or an estimation of the volume of the oil, yeah, and classify the type of oil and so on. Same company. This is oyster farms, also in France, in shallow water, where I'm not sure about what they are looking for in those oyster farms, but yeah, that's at least the application. But these guys as well doing bathymetry, right, with our sensors. This is again the same company. It's a very good application. They got the contract to fly the coral reefs in Madagascar 5 years in a row, to look at how the coral reefs are bleaching and dying out. So I think the whole campaign takes 3 months to fly. And they are as well diving with point spectrometers to gather yeah, ground samples and ground truth, basically. This is some kind of the 3 of the classified maps they are getting out, right, which is vegetation index, the kind of minerals, and yeah, the seaweed, algae, corals, and so on. Yeah, dryness stress again on a larger scale than before, also done by DLR in Germany. A lot of the German institutes that have purchased this part of the NMAP project, right? So it's where they use our data to simulate NMAP data. So DLR is one of those institutes, and GFZ as well. Yeah, inspection of mine face or mine walls. This is done together with GFZ as well in 2018, where you can fly the mine face like you do here and classify it instead of scanning. It's a new application, or kind of new application. You need to think differently from classical airborne images where you are typically looking straight down. Here you're looking 80 or 90 degrees to the side. So you need to work in 3D space instead of 2D space. Urban mapping, not sure where this is, but we can detect the time what you're looking at on the ground in very rough, not too many classes here. This is a demo we did in San Diego, I think maybe 3, 4, 5 years ago, where they have the eucalyptus trees, right, that are producing a lot of fire fuel. So they want to detect the fire fuel so they can, yeah, I don't know, remove it or rake it, like Trump said. Another demo we did in China for fire fuel and NDVI. So usually the demos we do are quite simple. We don't do advanced processing when we do a live demo, for example. But for this demo, we did we flew and we did real-time georeferencing and real-time fire fuel and NDVI classification. I think I have a video in the end here of a trial we did. Ocean plastics, very relevant topics these days. Of course, if you know your sphere sensor, it has to be floating on the water. If it's underwater, all the sphere energy is basically absorbed in the water. That's why also when you're working the sphere range, you would like to have direct sunlight and not clouds between the sun and the objects, because a lot of the energy will then be absorbed in the clouds. Camouflage detection. This is, I think this experiment was for 2005, where we flew a military campaign in Sweden, detecting hidden military targets together with FFI. We called HySpecs ASI in the past, Airborne Spectral Imager. Yeah, this is from the same campaign, but the slides are from FFI. We're looking at different kind of camouflage, natural camouflage and camouflage nets, and they are very interested in trying to detect also objects in shadows, right, that are hidden in the shadows. This is a campaign also we did with the FFI in Bardufoss, where we wanted just to show the search and rescue application, where we put some fans submerged in water and run anomaly detection just to detect it, right? So potential application for search and rescue could be people that don't have a thermal signature anymore, for example. Yeah, another search and rescue or anomaly detection applications. Yeah, submerged in water. Looking for objects submerged and divers and so on. So this was done very simply with just spectral angle mapper and anomaly detection. Yeah, another example of anomaly detection, missing persons in Østmarka in Oslo. You can see here the objects. Again, this is an CRX or anomaly detection image. Then some agriculture examples from 2XL. Yeah, when I was listening to your bios, then I think probably you know more about all these indexes than me, but I'll just present the images here. Yeah, so they have showing here. So this is a processed hyperspectral images. Yeah, probably mosaicked a few of the HySpecs images together to one image, right? And this is showing NDVI, ARI2, REP, and NDNI. Yeah, again, different indices. Yeah. More nice classified images or quantified images from 2XL. This is just RGB images showing 4 images before processing, and then the NDVI of those 4 images after processing. Larger scale. They have also been looking into wheat disease, like you see here on the right, detecting that from airborne. with a huge trial. Yeah, and yeah, you can see it's a campaign that has been done repeatedly during the summer to see how it evolves. Weed detection, again in a quite large scale, where they first scan high specs on ground to gather ground truth. They take the same camera, put it in the aircraft, remove the 4 optics, the 1 meter lens that they have mounted here, and can use the same instrument from an airborne platform and do the actual survey. Yeah, black grass plants per square meter is the units in this classified image or quantified image. Then it's forestry. That's the first slide I showed for airborne, where they are classifying tree species. Where they're using machine learning to detect the trees, the tree crowns, and yeah, combining it with spectral imaging to detect the species of the trees. Yeah, and also tree disease detection. We have done a lot on tree, or we have, our customers done a lot on tree diseases also in the past. The first airborne campaign we did for Skogforsk actually was in 2005 on this application. Yeah, more diseased or trees with diseases. You can see here on a lot of the applications I show, they use reflectance data. But for example, if you're working on anomaly detection and an application in that area, you don't need reflectance, then radiance is enough. So it's, yeah, you don't always need to convert your images into reflectance images. But if you're using spectral libraries, for example, then you need reflectance. Yeah, let's move on. There was more slides than I remember. Yeah, phenotyping. We actually have our own phenotype scanner as well for lab, which we have been selling a lot to seed manufacturer, where they're doing phenotyping in their drivhus. I don't know the English word, but yeah, and this is here done from airborne, and we actually also sold quite a few UAV systems for phenotyping. Soil properties. It's a big application in hyperspectral. There are like separate conferences just on hyperspectral soil processing. So yeah, chlorophyll content. Yeah, this was just a quick run through of some of the application I could gather from our customers. Now I just want to show, this is, I think this was a demo we did in 2018 for Total, just showing them that you can do real-time processing and real-time georeferencing from a UAV platform. So, and also from airborne. We had a big military project with also a collaboration between France and Norway called SISIF from 2009 to 2012. Where we developed a huge hyperspectral camera called Odin 1024. It weighs 100 kilos, together with a real-time processing unit that were doing real-time target detection while flying, and also then georeferencing and giving out the position of the targets, right? So of course we have used this now since that time, right? A lot has happened when it comes to processing power, and now you can do the same with a compact GPU, right, inside your UAV platform, which is what we're doing here. So again, here it's a live demo, virtual demo actually, with Total live on Skype, I think it was, where we are flying, filming, and showing the real-time georeferencing and the real-time processing. We're only showing NDVI and anomaly detection here. And this is one of our previous platforms that was delivered by CamFlight, now Nordic Unmanned. So this is just a view of the drone flying in the flight management software that's controlling the drone. And this drone uses a Lockheed Martin autopilot, so it's a quite expensive drone. On the right side here, you can see now the RTGeo. So this is rectifying or georeferencing the UAV images while you fly and just visualizing it. So now we are switching here between CRX and NDVI. The view you're seeing now is just a normal RGB image. This was flown in February, so you can see there's ice on the water. But you still will see we are switching now to NDVI. You can still see that there is some vegetation around the sea, the coastal area here. And now NDVI again, zooming in, you will see some vegetation. But again, it's February in Norway, so not too much chlorophyll. This just is kind of to show the potential. Right here, you can implement your own algorithms, and so on. I'll skip a bit ahead. The third flight land, we put out a gray bag on the rocks just to show an anomaly detection application, where it's easy to discriminate between the background and a man-made object. So that's the third flight line we are starting now. So this is mostly dark. Of course, the anomaly detection image, you need the threshold, right? So you're only showing objects that are of high probability of not being part of the background. And this is what we're showing now. So it's mostly dark until you reach the bag that's on the mount on the rocks here. Yeah. So that could be, for example, a camouflaged object in the forest, or missing persons on Hardangervidda, and so on. But just shows you that you can do it in real time from a very small, compact platform. Of course, small is also relative, right? This is the total solution here. The drone, camera, and everything weighs 22 kilos. Typically, a copter solution like this can fly for 25 to 30 minutes. You need a special permit to fly 25 kilo payloads in Europe and in the US, and a lot is happening now on the regulations to fly that. Before 2015, 50% of what we sold was for airborne. Today, airborne is both for aircraft and UAV, but probably there's a 50-50 combination between UAV and manned aircrafts today.